This tutorial covers some basic things you need to know about acids and bases, specifically the properties of acids and bases, their strength, at least relative to one another, and of course what conjugates are. So the first thing we'll talk about is what an acid and a base are. Then we'll talk about their properties, how we rank their strengths, and then of course, last but not least, conjugate acid-base pairs. All right, so let's define what an acid and a base are. I'm sure that in your life you've heard of things being acids or bases, but you might not have known exactly what that means. There are actually two definitions for acids and bases. The first one is the Arrhenius definition. The Arrhenius definition of an acid is any substance that produces hydrogen ion when you dissolve it in water. Before we get too far, I want to talk about you're going to hear hydrogen ions often referred to as a proton, and I want to explain what that means. So why can we call a hydrogen ion a proton? Well, when you have a hydrogen atom is made of a proton and an electron, just one of each. But when it ionizes and loses that electron, it becomes a hydrogen ion, which really is just one proton. So just know that you can use the word proton interchangeably with the word hydrogen ion. So an acid will produce protons or hydrogen ions when you dissolve it or them in water. So an example of that is HCl. HCl, whenever you drop an HCl into water, it actually dissociates into the chloride ion and these little hydrogen ions. And what makes HCl an acid is that it's producing, of course, hydrogen ions when you dissolve it in water. All right, so let's talk about the Arrhenius definition of a base. A base is any substance that when you dissolve it in water will produce hydroxide ions. So an example of that would be sodium hydroxide. When you drop it in water, it will dissociate into sodium ions and then hydroxide ions. So it's considered a base because it's producing these hydroxide ions. At least according to the Arrhenius definition, that's why it's a base. The problem with the Arrhenius definition is it's a really limited definition, especially the definition that we give to a base, because there are known bases, like for example ammonia, NH3, we know it's a base, yet it doesn't contain the hydroxide ion. So according to the Arrhenius definition, it doesn't necessarily do what the Arrhenius definition says, which is dissociate to produce hydroxide. It does, however, react with water to produce ammonium and a hydroxide ion. And how does it do that? That ammonia actually takes a hydrogen off of the water and leaves behind hydroxide. So it does actually produce hydroxide when you dissolve it in water, but the Arrhenius definition is a little bit confusing when you think about something like ammonia, which we know is for sure a base. So a second definition for an acid is the Bronsted-Lowry definition of an acid. And this is the one that we're going to focus on the most because it's a broader definition. It's a better definition than the Arrhenius definition of an acid, specifically for bases. So an acid, according to Bronsted-Lowry definition, is pretty similar to the definition for an Arrhenius acid. It's a substance that easily loses hydrogen ions to another substance. So in this example that I've written, you've got here acetic acid, and when you put it with another substance, in this case that substance happens to be water, it becomes an acetate ion. So you can see that as it goes from here to here, it's lost in a hydrogen ion. So that makes that your acid. Now, according to the Bronsted-Lowry definition for a base is any substance that easily accepts a hydrogen ion. So in this example up here, water became this, which is called hydronium. And it did that by accepting the hydrogen from our acid. So that makes water a base when it reacts with acetic acid. So let's do a quick example and see if you can identify the acid and the base in this reaction. So if you look at what you've got here, you've got carbonate ion reacting with HCl. And on the other side, bicarbonate and chloride ion. So what you need to look for is who lost a hydrogen and who gained a hydrogen. So we'll start with carbonate. Carbonate became bicarbonate or hydrogen carbonate on the other side. And it did that by accepting a hydrogen. And that makes hydrogen carbonate your base. I want to point out the charge difference. Remember, you're adding an H plus to, so a +1 charge to a -2 charge, so the charge on the resulting substance is going to be just a -1. And then on the other side, or on the other compound, this HCl became just chloride ion by losing a hydrogen ion. And again, if you think about the charge difference, you're removing a positive from this, so that's going to leave behind a negative. And that makes HCl your acid. All right, let's talk about the properties that acidic and basic things have. So let's talk about acids first. Acids, when you dissolve them in water, of course, give up hydrogen ions, and those hydrogen ions will conduct electricity. So acids will conduct electricity. And there's a word for that in science. Any solution that conducts electricity is called an electrolyte. Okay, the second thing or property that acids have is they change litmus paper to a red color. So what the heck is litmus? Litmus is a chemical indicator for acids and bases. So you can buy this paper called litmus paper that's treated with litmus, and you can buy it either in blue or red variety. Either one will give you the same result. I don't know why they sell them in two different colors. But any litmus, no matter what color it starts, if you dip it into an acid, will turn pink. We call it red even though it's pink, so you'll just have to get used to that. Acids tend to have a sour taste, so you can think about things that are sour, like lemons, limes. Those things are acidic. They tend to react with bases to neutralize their properties. We're actually going to talk about that in a little bit, or actually in the next video. So, we'll kind of talk about this a little more. And then the other thing about acids is that they tend to react with metals to give, and liberate hydrogen gas. What I mean by that is that, of course, that acids give up hydrogen ion. And then that hydrogen ion will tend to combine with other hydrogen ions and produce hydrogen gas. And acids tend to do that when they react with metals. And so what you really need to know is that they're corrosive to metals. You don't want to put acids down the drain, or at least really concentrated acids down the drain, because it'll eat through the drain pipes because they're often made of metal. And this is the same reason why when you throw up over and over and over, your stomach acid will actually eat through your teeth. I know that's really disgusting, but your teeth have a lot of calcium in them, and calcium is a metal, so the acids actually react with the calcium in your teeth and eat through the enamel. Basic properties. Bases are also electrolytes, conduct electricity. Bases tend to turn litmus paper blue, so when you dip, again, any color of litmus paper, no matter what color it starts, if you dip it into a base, it'll turn blue. They are slippery feeling, so think about things like soaps, shampoos, you know how they're very slippery? That's because they're basic. And they also, like I said, tend to react with each other, so the bases will react with acids to neutralize their properties. Something I'm going to add on here, number 5, if you eat them, which some of them you can't, they have a bitter flavor to them. So you can think of things that are bitter, and those things tend to be very basic. So here's some examples of things you would find around your house that are considered acidic. So beer, vinegar, juices, aspirin, some citric fruits, citrus fruits, and then some cleaning products, but not too many are acids, like I said, because if you put them down the drain, they eat through the pipes. And then bases tend to be, your cleaning products around your house tend to be made of bases because they won't react with the metal in your pipes. or any enamel or porcelain on your tubs, things like that. And then, of course, I tried to find a food that is basic. Green leafy vegetables, they're very bitter tasting because they're basic. So let's have a brief conversation about the strength of acids and bases. So sometimes acids are strong acids and sometimes they're weak acids, and the same is true with bases. And what makes them strong or weak is how much they actually give up hydrogen ions. So do they give them up really easily, like 100%, or do they give them up and then take them back and give them up and take them back? So there could be an equilibrium that is established where the acid or the base is doing its thing, either giving up hydrogen or taking it on, and then, of course, reversing the process. So this acid right here, this is acetic acid, this is vinegar. When you put acetic acid in water, you're going to get a reaction where it gives up its hydrogen to become acetate ion, and then, of course, the hydrogen goes to the water to become hydronium. But those two things don't just hang out like this. Sometimes then when they bump into each other, the water or the hydronium gives its hydrogen to the acetate to go back to being acetic acid. And then, of course, when the hydronium gives up a hydrogen, it becomes water. So it establishes an equilibrium. So I could write the expression for that equilibrium. Notice I left water out because water is a pure liquid. And this becomes what is called our Ka value. And so instead of just calling it a Keq, we call it a Ka. And I hope you realize the A stands for acid. And the Ka value for acetic acid is 1.8 times 10 to the negative 5. That's a really small number. I mean, it's 0.000018. That tells me that I don't have a lot of my products in my system, and I have a lot more of my acid before it dissociated. So that tells me that this doesn't dissociate 100% in water. And then there's hydrochloric acid, HCl. When I react it with water, it reacts in one direction to produce hydronium and chloride ion, and there is no reverse reaction. So if we were to write a Ka or to calculate a Ka for hydrochloric acid, what we would end up getting is a really large number because hydrochloric acid dissociates to produce these two things and it doesn't go backwards. So you get all products and there are no reactants left in your system. So strong acids will dissociate 100%. There is no equilibrium. And weak acids don't dissociate 100%. So you get an equilibrium and therefore you can have Ka values. So some examples of strong acids are hydrochloric, hydrobromic, hydroiodic, perchlorate or perchloric acid, sulfuric acid, and nitric acid. Every other acid is pretty much weak. And the same rules, of course, apply for bases. So something like lithium hydroxide, when I dissolve it in water, it dissociates 100%. That means that, of course, it gives up, or its ions split into lithium and hydroxide, and there is no backwards reaction. So its Kb value is like really, really big. In fact, I don't even think there is a measured Kb value for lithium hydroxide. Whereas ammonia, when it acts as a base, it's taking a hydrogen from water to produce hydroxide and ammonium ion. And its Kb value is actually less than 1, so it's really small. I don't know the exact value. And of course, hopefully you realize the B for its equilibrium constant just means base. At this point, it would be a good idea to have a conversation about substances that are amphoteric. Amphoteric is a substance that can either give up hydrogen ions and act as an acid or take on hydrogen ions and act as a base. And it really just depends on the strength of the other thing that you put it with. The most famous, of course, amphoteric substance, maybe you haven't realized this yet, is water. So if I put water with a weak acid, like acetic acid, it actually will act like the base and take a hydrogen from the acetic acid and leave behind an acetate ion So it acts in this case as a base by accepting a hydrogen ion. You can also put water with something that's a known base, like carbonate ion. And it will actually give its hydrogen to the carbonate ion to produce bicarbonate and hydroxide. And so in this case, the water is acting as an acid by giving its hydrogen up. And really interestingly, water can actually ionize itself, which sounds totally weird, but when you have like a container of water, you actually have an equilibrium going on where one water is actually taking the hydrogen from the other and producing hydronium and hydroxide. You can actually shorten this equation by just writing it like this. So you're just showing this water splitting into hydrogen and hydroxide, and of course there's a reverse reaction. We give a special sort of K designation for water's equilibrium value, and we call that Kw. And the Kw of water, of course, is equal to hydroxide times hydrogen ion concentration, or you can say hydroxide, forgot the negative on there, sorry, times hydronium concentration. It's going to be the same thing. And that value, it actually has a number that's measurable, 1 times 10 to the negative 14. So you need to know the Kw for water. And finally, we will talk about conjugate acid-base pairs. So by now you should know that an acid gives up hydrogen and a base will take on a hydrogen. And the fact is that acids are only going to give up hydrogen if there's something there to take it, and bases are only going to take on hydrogens if there's something there to give it. So as an example, you might have something like hydrogen fluoride and ammonia. And hydrogen fluoride will readily give its hydrogen up to ammonia to produce NH4 and leave behind a fluoride ion. So in this example, hydrogen fluoride is your acid because it gave up a hydrogen, and ammonia, because it's taking on that hydrogen, is your base. But because this is reversible, that means in the reverse reaction, the opposite is taking place. So your fluoride ion is actually taking on a hydrogen. So that makes your fluoride in the reverse reaction a base, and the ammonia is actually taking on, or rather giving up a hydrogen, and that makes it an acid. So to keep this all straight, so we don't just say, hey, that's the acid and that's the base, and because there are 2 acids and 2 bases in this reaction, we have what are called conjugates. So we actually call, instead of this just calling it a base, we call it a conjugate base. And this is your conjugate acid. So in the forward reaction, there's an acid and a base, and in the reverse reaction, there's a conjugate acid and a conjugate base. And the conjugate acid-base pairs are the things that differ from each other by 1 hydrogen. So that means hydrogen fluoride and fluoride ion are your conjugate acid-base pair because they differ by the presence of only 1 hydrogen ion. Ammonia and ammonium differ by 1 hydrogen ion and are therefore conjugate acid-base pairs as well. So I not only will have you identify acids, bases, and conjugate acids and conjugate bases from an equation, but I might ask a question like this. What is the conjugate acid of HCO3 minus? So notice I've asked you for the conjugate acid of this substance. So that hopefully clues you in to the fact that this substance is acting as a base, and so its pair is going to be a conjugate acid. So they have to differ by 1 hydrogen ion, and the conjugate acid has to act as an acid. So it would be H2CO3, because H2CO3 would be an acid. In fact, it would be the conjugate acid of HCO3 minus, because for this to become this, it has to give up a hydrogen ion, and so it's an acid. So those are conjugate acid base pairs. And that brings us to the end of this presentation on acids and bases.